Welcome to an introduction to the derivatives of hyperbolic functions. We will also discuss the integrals of many hyperbolic functions. Recall the definitions of the hyperbolic functions in terms of exponential functions. The hyperbolic cosine is equal to e to the x plus e to the negative x divided by 2. The hyperbolic sine is equal to e to the x minus e to the negative x divided by 2. The hyperbolic tangent can be thought of as the hyperbolic sine divided by the hyperbolic cosine, which is equal to e to the x minus e to the negative x divided by e to the x plus e to the negative x. The hyperbolic cotangent is the reciprocal of the hyperbolic tangent, which is equal to e to the x plus e to the negative x divided by e to the x minus e to the negative x. The hyperbolic secant is the reciprocal of the hyperbolic cosine, which is equal to 2 divided by e to the x plus e to the negative x. The hyperbolic cosecant is the reciprocal of the hyperbolic sine, which is equal to 2 divided by e to the x minus e to the negative x. Now, let's look at how we can use these definitions to find the derivatives of the hyperbolic functions. Let's look at finding the derivative of the hyperbolic cosine function. So the derivative of the hyperbolic cosine function is the same as the derivative of e to the x plus e to the negative x divided by 2. That is the same as 1/2 the sum of the derivatives of e to the x and e to the negative x, which is equal to 1/2 e to the x minus e to the negative x, which is the same as e to the x minus e to the negative x all divided by 2, and that equals to the hyperbolic sine function. We can similarly find the derivatives of the hyperbolic sine function. And we can then use the exponential definitions or the definitions of the other hyperbolic functions in terms of the hyperbolic sine and cosine to find the other derivatives. From this table, you can see that the derivative of the hyperbolic sine function is the hyperbolic cosine function. The derivative of the hyperbolic cosine function is the hyperbolic sine function. The derivative of the hyperbolic tangent function is the square of the hyperbolic secant function. The derivative of the hyperbolic cotangent function is the negative of the square of the hyperbolic cosecant function. The derivative of the hyperbolic secant function is the negative of the product of the hyperbolic secant function and the hyperbolic tangent function. The derivative of the hyperbolic cosecant function is the negative of the product of the hyperbolic cosecant function and the hyperbolic tangent function. You should note that there are similarities but also differences compared to the derivatives of the trigonometric functions. Namely, the difference is the sign of the derivatives. Let's look at a couple of examples involving the derivatives of hyperbolic functions. For this first function, our first example, you are to find the derivative of y equal to x times the hyperbolic sine function. For the solution, we will use the product rule of the derivatives. This gives us that the derivative of the function would equal to the derivative of x times the hyperbolic sine function of x plus the derivative of the hyperbolic sine function of x times x. That gives us 1 times the hyperbolic sine function of x plus x times the hyperbolic cosine function of x. Simplifying that, we have the derivative is the hyperbolic sine function of x plus x times the hyperbolic cosine function of x. For another example, let's find the derivative of y equal to the hyperbolic secant of x squared. For this problem, we will use the chain rule. This gives us that the derivative of the this gives us that the derivative of the function is equal to the negative of the hyperbolic secant of x squared times the hyperbolic tangent of x squared times the derivative of the inside, which is 2x. Rearranging this a little, we have the derivative is negative 2x times the hyperbolic secant of x squared times the hyperbolic tangent of x squared. As we have seen before, when we're discussing the relationship between the derivatives and integrals, we can create the following table illustrating the relationship between the derivatives of hyperbolic functions and their corresponding integrals. Again, as mentioned before, while there are similarities between the derivatives of hyperbolic functions and trigonometric functions, you must remember the differences as well. So the integral of the hyperbolic sine of x is the hyperbolic cosine of x plus c. The integral of the hyperbolic cosine of x is the hyperbolic sine of x plus c. The integral of the square of the hyperbolic secant of x is the hyperbolic tangent of x plus c. The integral of the square of the hyperbolic cosecant of x is the negative of the hyperbolic cotangent of x plus c. The integral of the product of the hyperbolic secant of x and the hyperbolic tangent of x is the negative of the hyperbolic secant of x plus c. The integral of the product of the hyperbolic cosecant of x and the hyperbolic cotangent of x is the negative of the hyperbolic cosecant of x plus c. Now let's look at one example of an integral involving hyperbolic functions. For this example, you are to find the integral of the square of the hyperbolic cosecant of the square root of x divided by the square root of x dx. To solve this problem, we will use substitution by letting u equal to the square root of x. This gives us du is equal to 1 divided by 2 times the square root of x dx. By doing the substitution, we get the integral is equal to 2 times the integral of the square of the hyperbolic cosecant of u du. Integrating that, we get negative 2 times the hyperbolic cotangent of u plus c. Back substituting, we get the answer is negative 2 times the hyperbolic cotangent of the square root of x plus c.